In 5.1, we're looking at length and dot product. So first up, let's look at the length of a vector and how to find a unit vector. So let's see, the length of a vector. I've got two examples here. Let's call this purple one U and the blue one V. So if you wanted to find the length of these vectors, it's the same as finding the distance from here to here. So you could use the distance formula. You could also use the Pythagorean theorem. This rectangle here, this length is 2, and this length down here is 1, 2, 3, 4. So by the Pythagorean theorem, we know that the length of U, we use double absolute values to denote the length of U. It's going to be the square root of 2 squared plus 4 squared. So that's the square root of 20, which is the 2 root 5. So notice really all we did there was, this was the point 4, 2. So we wound up squaring the 2 and the 4, adding them together, and that's what the Pythagorean theorem gives us. For this V down here, if we want to find the length of V, it's going to be the square root of this side length plus this side length. So what are those? This one is 1, 2, 3, 4, 5. And the other one is 1, 2, 3, 4. Wait, I lost count. 1, 2, 3, 4, 5. I don't think that other 5's right. I made it all messy with this. Let's count that again. Down here, this is 1, 2, 3, 4. All right, so this one's going to wind up being square root of 16 plus 25. So that's square root of 41. So we're just using the Pythagorean theorem here. And notice what it winds up giving us is whatever the coordinates are here, 4, 2, and down here this was the point 5, negative 4. What we wind up doing there is just squaring the two coordinates, and it doesn't matter if they're positive or negative, because when you square, you get a positive. So you can generalize this easily for a vector in Rn. The length of a vector in Rn, it's also called the norm, is this. You just square all of them, add them up, take the square root. So let's do a couple of examples here. Actually, we'll do 3 examples. So for this one, the length of this vector is going to be the square root of 6 squared plus 2 squared plus 3 squared. So that's the square root of 49. So that's 7. All right, length of this one is going to be square root of 4 squared plus 4 squared plus 1 squared plus 5 squared. What's that work out to? 32, 33, 43, 53, 58. Can that be simplified? No, because 58, you could factor a 2 out of it. It'd be 2 times 29, and you can't simplify that. All right, and then this last one, I don't know if you can hear my cat. She's walking around meowing, wanting attention. Let's see. Square all these. You square the first one, you get 3, 64, 49, 0, and 5. Let's see, what is that? 3 plus 64, that's 67, plus 49, plus 5. Well, that's nice. This gives us a 121, which is a perfect square, gives us 11. All right, so that's really all there is to finding the length of a vector. Now let's talk about unit vectors. A unit vector is just a vector with length 1. So, the first things you'll probably think of if you think of a unit vector would be things like the standard basis vectors. Like this is a unit vector. This is a unit vector. But so is this. Really, anything that lies on this circle. So in R2, unit vectors are the ones that lie on the unit circle. And in R3, it would be anything that lies on the unit sphere. So one question people ask a lot of the time is, here's a vector, find a unit vector that's in the same direction. And the way you do that is you just take the vector and you divide it by the length of itself. So right here it says, if v is a non-zero vector, then the unit vector you get by doing v divided by its length has length 1 and is in the same direction. And I'll go ahead and mention up here, negative u is a unit vector in the opposite direction. So let's look at this example here. Find the unit vector A in the same direction as 12, negative 5, and B in the opposite direction. All right, so we don't have to draw this out. We could just do it quickly, but I want to actually draw it. So 12, negative 5. I'm not going to worry about getting it exactly to scale, but it's going to be, something like this. 12, negative 5. So a unit vector in the same direction is going to be something like just, much shorter, but pointing in the same direction with a length of 1. So what's the length of this thing? Let's see. The length of v is the square root of 12 squared plus negative 5 squared. So that's 144 plus 25. So that's 13. So the vector that's the unit vector in the same direction is going to be, we just take this over here and divide it by 13. So unit vector in the same direction that's what part A wanted, is going to be 12 over 13, negative 5 over 13. And for B, a unit vector in the opposite direction, that's going to be this guy here, pointing in the opposite direction. And the only thing that changes there is the signs. So for part B, it's going to be minus 12 over 13, then positive 5 over 13. That's all there is to it. Let's see, problem 122. This is asking us really the same thing, only this time it's a vector in R4 instead of in R2. But we'll do the same thing. First, find the length of this vector. The length of u is going to be square root of, I'm just going to go ahead and square these as I go. 3 squared is 9, negative 1 squared is 1, 2 squared is 4, and 4 squared is 16. So what do we get there? That adds up to 30. So for the one in the same direction, that's going to be 3 over root 30, negative 1 over root 30, 2 over root 30, and negative 4 over root 30. And I am not picky at all about having radicals in the denominator. Leave your answer like that. The other thing you could do is you could, if you wanted to, you could just write 1 over root 30 and then copy the original thing down there. That's just as good. All right, speaking of copying things, we've got to do part B. And here's my answer to part B. Almost. B is supposed to be a unit vector in the opposite direction, so all we have to do is go through and change the signs here. So let's see, that means this becomes negative, this becomes positive, it's negative, that's positive. I'm going to go back and delete these pluses since we don't really need them. All right, so that's A and B.